As SpaceX continues on its journey to get the Starship ready for human flights, we often forget that getting the rocket off the ground is not the hardest part of its journey. The real challenge will be getting it to land smoothly on a desolate Martian landscape. So, how will SpaceX attempt this ambitious endeavor? Can the Starship safely land on Mars with humans on board? Let's find out. The liftoff. The SpaceX Starship stands as humanity's primary prospect for landing on Mars during your lifetime. The distinctive quality that renders the Starship exceptionally suitable for this mission is its remarkable power. Undoubtedly, future iterations of the Starship will possess substantial capability to transport both crews and substantial supplies on their journey to Mars. While ascending presents its own set of challenges, the descent onto the Martian surface poses the most intricate maneuver of the entire journey. This critical moment can either ensure success or lead to failure. The complexities involved in mastering this descent are more extensive than one might initially consider. Before delving into the intricacies of landing on Mars, it's essential to understand how the Starship reaches its destination. The key concept to remember in space travel is that everything is in constant motion. In the solar system's context, all celestial bodies orbit the Sun. Earth is currently held in the Sun's gravity well, and our orbital velocity, approximately 30 km/s, prevents us from falling deeper. We're essentially traveling at this speed in a circular path around the Sun, completing one orbit every 365 days. Mars, being farther from the Sun than Earth, isn't as deeply entrenched in the gravity well. Consequently, Mars can maintain a slower orbital velocity of around 24 km/s. To embark on interplanetary journeys, like reaching Mars from Earth, we need to recognize that leaving our planet means becoming another object within the Sun's gravity well. If we were to decrease our orbital velocity, we'd start descending into the gravity well, altering our orbit towards an inner planet like Venus. Conversely, accelerating beyond Earth's velocity would propel us upward in the gravity well, shifting our orbit towards an outer planet such as Mars. Traversing the solar system boils down to altering our velocity relative to our starting point. The term we use to express this concept is delta V, where delta signifies change and V denotes velocity. Delta V is typically measured in kms. For instance, if Earth is moving at 30 km/s and you accelerate your spaceship to 31 km/s, you've achieved a delta V of 1. Similarly, if you decelerate your spaceship relative to Earth and travel at 29 km/s, you also have a delta V of 1. However, simply blasting off from the Earth's surface at 1 km/s won't propel you upward through the solar system. Gravity and atmospheric drag will keep you tethered to Earth, affecting the delta V required for maneuvering the spaceship. This gravitational force, coupled with atmospheric drag, poses a significant challenge in transitioning from Earth's surface to outer space. Achieving a typical low Earth orbit demands a delta V of approximately 4 km/s. This substantial acceleration underscores why the Starship relies on the immense power of the Super Heavy booster during launch. It's also the reason why the Starship pauses for a refueling session in Earth orbit before continuing its journey to Mars. Additional delta V is needed to complete this interplanetary trip. Fundamentally, altering velocity requires propulsion, and propulsion necessitates fuel. The benefit of refueling in orbit lies in resetting our starting point. From this point, we only require an additional 5 km/s of delta V to reach the surface of Mars, which is roughly equivalent to the change needed to escape Earth's atmosphere. However, the approach for the next leg of the journey differs significantly. While escaping Earth involves speeding up, landing on Mars demands a substantial amount of slowing down, a task that can be just as challenging. A fully fueled Starship in low Earth orbit is estimated to have enough thrust for approximately 6 to 7 km/s of delta V. Although this falls short of the 5 km/s needed to reach Mars, the same forces that complicated the Earth's escape, gravity and aerodynamic drag, now work to our advantage during the landing, effectively increasing the Starship's delta V potential. The journey. Here's the breakdown. In orbit around Earth, even a few hundred kilometers above the surface, we are firmly within Earth's gravity well. Our velocity is the sole factor keeping us aloft. If the Starship were to decelerate, it would start descending back towards Earth. Conversely, by accelerating, we continue rising into space. Due to our proximity to Earth, a substantial delta V is required to counteract gravity. The ship needs to accelerate by 44 kilometers per s to reach geostationary orbit and an additional 68 kilometers per s takes us to the height of the Moon. Upon reaching this point, we are on the edge of Earth's gravity well. While gravity is infinite, its influence diminishes as we move further away. Another 9 kilometers per s of velocity is needed to completely escape Earth's influence. From this position, floating in the vacuum of space beyond the Moon, only 39 m per s of delta V is required to achieve our Earth to Mars transfer velocity. This second leg of the journey consumes approximately 6 kilometers per s of delta V, utilizing at least half of the potential energy in our Starship, if not more. Consequently, we lack sufficient fuel to land on Mars using engines alone. Now, we face the challenge of addressing the fact that the velocity gained to escape Earth's atmosphere and gravity well has set us on a significantly higher speed around the Sun compared to the planet Earth, which was already traveling at 30 kilometers per s to begin with. In contrast, the planet Mars orbits at a speed of just 24 kilometers per s, indicating that we are moving considerably faster than our target planet. Without corrective action, we risk overshooting Mars and finding ourselves stranded in the asteroid belt. After coasting through the vacuum of space for several months, our first task is to execute a deceleration burn. Flipping the Starship around and reactivating the Raptor engines, we must shave off 67 kilometers per s of velocity to become captured in the gravity well of Mars. This marks the initial step in what promises to be a challenging journey. Another burn of 34 kilometers per s brings us to the height of the outer Moon, Deimos, and an additional 4 kilometers per s of delta V gets us down to the inner Moon, Phobos. However, slowing down to this extent has already consumed over 5 kilometers per s of the potential delta V in our fuel tanks, leaving us with roughly 1 to 2 kilometers per s remaining. Yet, we require at least another 5 kilometers per s of delta V to safely reach the Martian surface. In theory, achieving this is possible, provided we strategically utilize our remaining fuel. It's crucial to acknowledge that everything beyond this point is purely speculative, as there is no confirmed method that will be used. One way it could be done is to conserve fuel for the landing burn, leveraging external forces to slow down our ship. Entering a circular low Mars orbit would deplete most of our remaining fuel, so an elliptical orbit proves more strategic. In this scenario, we move in an oval pattern with a low point, perigee, close to the planet, and a high point, apogee, deeper into space. This maneuver allows us to leverage both aerodynamic drag and Mars gravity to aid in slowing down. Although the Mars atmosphere is thin, utilizing any available help becomes crucial. Lowering the perigee carefully, the ship dips into the upper atmosphere, benefiting from atmospheric drag and losing a small amount of velocity before being flung back out to the apogee. If executed properly, the gravity of Mars will pull us back in to repeat the process. During each atmospheric dip, we accumulate more of the crucial delta V, steadily approaching the velocity necessary for a gentle touchdown on Mars's surface. However, this maneuver cannot be sustained indefinitely. At some point, we must transition from a shallow dip to a full-on dive through the Martian atmosphere. The landing. Achieving a landing trajectory for Mars poses challenges due to the planet's smaller size, about half that of Earth. Consequently, the angle of attack required to descend below the Martian sky is relatively steep. This necessitates a significant amount of energy, pushing the vehicle down to prevent it from skipping off and rebounding into space. Since we aim to conserve our engines until the last possible moment, the force needed to push the ship deeper into the atmosphere must come from an alternative source. The 2016 SpaceX design for an interplanetary transport system featured an aerodynamic lifting body on the upper stage. Although the Starship is smaller than its predecessor, the methodology remains similar. On its final approach, the Starship flips over and enters the atmosphere upside down, with the belly and tail pointing up and the nose pointing down. This orientation leverages the lift generated by the body, pushing the vehicle toward the surface on a steeper angle. As entry progresses, aerodynamic drag contributes to a substantial loss of velocity, Once the angle of attack is set, the Starship executes the more traditional belly flop maneuver seen on Earth. This approach maximizes drag to reduce velocity. However, this aerodynamic force has its limitations. The maximum speed of freefall, known as terminal velocity, is reached when the drag and buoyancy of the falling object equalize with the force of gravity. To overcome terminal velocity, a parachute is employed, significantly increasing drag and slowing down the descent. Starship won't rely on parachutes, so there will be a point where the aerodynamic drag has maximized its effect, and the vehicle reaches terminal velocity. Due to the thinner atmosphere on Mars, terminal velocity is approximately 5 times faster than on Earth. In other words, the delta V achieved by belly flopping through the Martian atmosphere is only 1/5 of what Starship accomplishes on Earth. Consequently, more engine power is required to land on Mars compared to Earth. Assuming everything has gone smoothly up to this point, Starship's engines will fire up one last time, flipping the tail towards the surface. At this moment, the fuel in the rocket's header tanks will provide the necessary delta V to precisely synchronize the ship with the surface of Mars, enabling a soft touchdown. This complex landing process leaves zero room for error, emphasizing the tremendous difficulty of landing a massive vehicle like Starship on Mars. NASA finds it easier to land smaller, lighter vehicles on Mars because the potential delta V of fuel is influenced by the vehicle's mass and engine efficiency. Lighter ships achieve more change in velocity with a pound of fuel compared to heavier ones. However, there's a limit to the amount of fuel that can be transported to Mars. While it would be easier to land a lighter Starship on Mars, SpaceX's ambitious goal of building a self-sustaining city of 1 million people necessitates the current size of the spacecraft. SpaceX is actively working on enhancing the delta V of Starship by planning to make Starship V2 longer, with larger fuel tanks while simultaneously reducing its weight. Additionally, 3 more Raptor vacuum engines will be added, and the upcoming third version of the Raptor is expected to offer higher efficiency, providing increased delta V potential. There are other long-term solutions to consider. Mars's outer moon, Deimos, requires a more manageable delta V of around 3 kilometers per s to move from low Earth orbit to its orbit. This presents an opportunity to establish an outpost, or a Mars gateway, at the orbit of Deimos. Such a station could serve as a refueling point, allowing the spacecraft to tackle the most challenging part of the journey with an ample reserve of delta V. This strategic approach introduces a margin of error that significantly enhances the safety of a Mars landing, making it a more feasible and reliable option. Landing a fully loaded Starship on Mars poses logistical challenges that border on the extraordinary. SpaceX faces uncertainties and potential failures in their pursuit of this ambitious goal, similar to the challenges encountered during the development and testing phases of Starship launches, which resulted in mid-air explosions. Learning to land on Mars is likely to be an iterative process with failures preceding success. The endeavor demands an exceptional degree of determination and resilience to persist through setbacks and failures. Attempting to land with people on board further amplifies the complexity and risk involved. Describing this mission as ambitious is, in fact, an understatement. What do you think? Can SpaceX replicate its success on Earth and pull off reliable Starship landings on Mars? Share your thoughts in the comments below.